Hello and welcome again to another video on number theory. Today we will talk about the Sieve of Eratosthenes. The plan for the video lecture will be to give you some background first, a Sieve version 1, which is probably something that you have seen before, the version 2, which is the actual version that was given by Eratosthenes. I'm going to explain the algorithm and how it works. And I'm gonna give you an implementation in Pari GP of that algorithm. And the timestamps will be in the video description. Now, what is the Sieve of Eratosthenes? So in general, is an algorithm to find all primes less than or equal to some natural number, and the natural number will be bigger than 2. The reason for that is because if n is less than or equal to 2, then it's just trivial to find that list. And always we are looking for primes that are positive prime numbers in all these cases. Now the algorithm is attributed to Eratosthenes of Cyrene. That's why the name Sieve of Eratosthenes, and this is a philosopher mathematician from the same time of Euclid. And the first known reference to that specific algorithm done by Eratosthenes was from a book called Introduction to Arithmetic from the 60 AD. And that picture that you see right there is one of the books that reprints in Arabic. So this is basically an old algorithm from more than 2,000 years ago. Now, what is it called Sieve? So Sieve is something like you see right there. It's just basically filter out the small portions from the big portions. So why is it called Sieve? So we're going to consider, for example, the composite number as big in the sense that they have more than 2 divisors, and the prime numbers will be considered as small in the sense that they will have only 2 positive divisors. So that's the idea for the sieve.
Suppose you throw all the numbers from 1 through 12 in the sieve, and you want to filter out the prime numbers. So that's why it's called a sieve. So only the prime numbers go through the holes of the sieve.
Now, this is the algorithm you probably have seen on the web, which is not the original algorithm that Eratosthenes came up with. The algorithm is you start with the list of numbers starting from 2 to n. Remember, the idea is to get all the prime numbers less than or equal to n. So we start from 2 because that's the first prime number, 2, 3, and so on. So we're going to declare one of the numbers a prime number, and usually what you do, you start with the number p equals to 2, which is the first one in the list, and you're going to cross out or delete all multiples of that p except for p from that list. So in the first case, you're going to delete all the multiples of 2 from that list. I will give you an animation on how this works. Now, find the next number in the list after you have done that, after that p, that is not yet crossed off, and set that to the new p, and then repeat. So you go back and repeat this step number 2. And you're going to stop this cycle by whenever your number p is bigger than the square root of n, and I will explain why is that. So let's look at an example, for example, for n equals to 100. So we will find all the prime numbers less than or equal to 100, and we will stop the algorithm when we set our prime equal to a number that is bigger than 10.
So suppose you're going to start with a grid of a 10 by 10 because we want all the numbers from 1 through 100 in that grid. Now, it is not necessary to make it a square. It's just a little bit pleasing. If it's not a square, you can make it in any arrangement. It doesn't matter. It just looks better a little bit if it is a square. So the first thing we do is we're going to fill out all the square with the numbers from 1 through 100. Now, of course, 1 is not a prime number, so we don't care about that one. And remember, the first thing we do with the algorithm is we're going to choose p, which in this case is going to be the number 2. And then we look at all the multiples of 2 that are there in that list. So let's mark that down with purple. Now those numbers are of course not prime because they are divisible by 2. And so they will have another divisor other than themselves in the number 1. So then we delete them from the list. Now the next number would be 3. That will be the next prime number. And now we find all the multiples of 3. Now all the multiples of 3 less than 100 is that list that you see there. Now one thing to notice is that 6, 12, 18, 24, they were already deleted from the list because they were also multiples of 2. So we don't actually delete them again. Now in this case, if you do it with pen and paper, you will have to cross out those numbers twice. And some numbers will be crossed out several times. But in this case, because I'm deleting them, then I don't have to do that. So we're gonna delete the ones that are multiples of 3, but are not multiples of 2 from that grid that you see there. So we delete them. Now we go to the next number, P, which is gonna be 5, and we look at all the multiples of 5. So all the multiples of 5 less than 100, again, as you can see there, 10, 15, 20, 30 are multiples of 5 that were already deleted from the list because they were multiples of either 2 or 3. So the ones that are in purple are the ones that were not deleted yet. So those are the ones we're gonna delete right now. Now we continue into the next one. So that will be 7. Remember, we have to stop once we reach P bigger than the square root of 100, which is 10. So 7 is still okay. So we will look at the multiples of 7. Less than 100, and those are the ones that you see there. Now 14, 21, 28, and so on were already deleted because they were either multiples 2, 3, or 5. So the only ones that are left are 49, 77, and 91. So we get rid of those. And now we stop right here. We don't keep deleting things because if we choose the next one, it's going to be 11, and that will be bigger than the square root of 100, which is 10. So with this lip, you just stop right here. So whatever is left is the collection of all the prime numbers that are less than or equal to 100. So that will give us all the list that we were looking for. So this is the procedure that you will follow for finding the prime numbers less than 100 or any other number. You will have to make a little bit bigger grid in that case.
So what is the original algorithm? So the original algorithm of Euclid is very similar to the one I just gave you, but it has a little bit of an improvement in the sense that you don't start with all the multiples of P, you start a little bit later. So you start still with the same list from 2 to n, and you select a prime number, which is in this case again is 2, and you cross all delete all multiples of 3, but only starting from P squared. Now this is a little bit of an improvement because you don't have to say 2p, 3p, 4p, and so on. The reason you can start from here is because if you have the list 2p, 3p, and so on, those numbers were already crossed off when they were considered multiples of 2, 3, and so on. So you can start from p squared. And we continue in the same way we did with the other algorithm. So we find the next number in the list, we call it P, that is not yet crossed off, and we set that number to be our prime number, and we repeat again the second step here, number 2, and we stop the algorithm when P is bigger than the square root of n. Now, this is very similar to the first one, and this is the actual original, the one that appears in the literature, but starting from P squared.
So the same similar animation is going to happen when you apply the original algorithm from Eratosthenes. We still have the grid. We still fill out the numbers from 1 to 100 because that's the one we are doing. We delete the 1 again. We start with 2. But now, so we look at the multiples of 2 that start at 2 squared. So in this case, it's 4, so we delete them. So that first step was not different. Now for number 3, we're going to look at all the multiples of 3 less than 100, but we start at 9 because if you look at 6, 6 was already deleted with number 2. So this is a little bit of a improvement. The original one from Eratosthenes is not a really big improvement really, but it's a little bit of an improvement anyways. So we continue the same way. So we delete those. Now the next one is 5, of course. And we're going to start the multiples of 5 at 5 squared. So which is 25. So that I don't need to compute the other multiples of 5, like for example, 10 or 15, because they were already deleted in the previous step. So it's a little bit of an improvement. Not much, but a little. So we still delete that. 7 again. So we start multiples of 7 at 7 squared, which is 49. And so the other multiples of 7 we were already deleted in the steps for primes 2, 3, and 5. So we delete those now, and then we stop here because we already reached a point. If I go a little bit further, I'm gonna be over the square root of 100. And I wanna stop here. So those are the numbers that we saw earlier, and exactly the same animation that we saw for the first part. So we still get the same list. It's just a little bit of an improvement over the one that we saw with all the multiples.
So why does the algorithm stop when p is bigger than square root of n? So let's discuss that idea. Why is that? Why not go all the way up to n? So let's look at that. So the answer to that question is based on the following theorem. So the theorem says that any composite number has a proper divisor less than or equal to the square root of n. The proof is like the one we did in a video, which I'm going to put in the upper right corner and also in the video description for you to check out. So what is the idea? So let's look at this. So we have this list of the numbers from 2 through n, and square root of n is going to separate that list between the ones that are less than or equal to the square root and bigger than the square root. So let's assume you have a composite number m, which is bigger than the square root of n. Now, by the theorem, m will have a proper divisor d, which is less strictly or less than or equal than the square root of the number. But the square root of m is less than the square root of n because m is right here in this position. So that d that you see there is going to be less than the square root of n. So because d is in this position right here, then that means that this number will be deleted from the list already just by looking at the numbers that are less than the square root of n. So that's the idea. That's why you only need to go up to the square root of n. So why does the algorithm work? Well, one of the reasons is because we got the square root, and also because at every step in the algorithm, what you're actually doing is the numbers that have proper common factors are deleted from the list. So the only ones that are left are the ones that have to be primed. Those are the ones that don't have, that have only one in themselves as the divisors, only two positive divisors. And because we only go up to the square root, we are sure that we are deleting all of the ones that are not prime. So how is the implementation in Pari GP? So I'm going to give you an idea of the algorithm first. So the algorithm, the original algorithm, is the list that I just showed you right there. So I'm going to turn this into a little bit of a explanation about the code. So I'm going to start with this list here, number 1. And once we do that, then we're going to define a variable, which I'm going to call list, which is the collection 2 through n. Now I'm going to initialize the variable p, which is initialized at 2, which is what the algorithm says. And you calculate all multiples of p starting from p squared. I'm going to call that multiples. That's going to be a list. And this will be the list. P squared plus p, p squared plus 2p, and so on. P squared plus kp. All of this will be has to be less than or equal to n, because we only go up to the multiples less than or equal to n, because we are looking at that limit. So we have that variable, that list. Now we're gonna update that list. Our list is gonna be the previous list, and we're gonna delete the multiples. Now that minus sign that you see there is a difference of set. So what that means is I'm gonna take this list and I'm gonna delete from that list the multiples of p starting from p squared. And another variable is going to be position. That's going to one is going to determine what's going to be my p. Remember, p starts at 2, so this number 2 will be position 1. This will be position 2, and so on, depending on what position you are in the list. So I'm going to keep position of that number there, so to keep track of what is the prime that I'm using to find the multiples. And the algorithm is going to stop when p is bigger than not equal to square root of n. So the while, we're going to use a while loop for that, and the while loop is going to work for p when it's less than or equal to the square root of n. So let's see how do we implement this in Pari. So let's look at the code. So I'm going to define a function which I'm going to call Sieve Era, and the name here is not actually very important. You can call it whatever you want. Usually a descriptive name is good to give you an idea what the function does. So this is going to be as an input, is going to be a natural number n, and because it's going to be a function that's going to have several lines of code, we're going to enclose that between these two curly brackets. So here I'm going to use several variables, which I mentioned in the explanation. To look at local variables, you're going to say my, and between this parenthesis and this parenthesis right here, you're going to put your local variable. So one of my first local variables is all the numbers from 1 to n, which you can write down like this in Pari GP. You initialize the first prime at 2. Multiples is the list of all the multiples of p, which I'm not going to initialize here. I'm going to do it later. And position is but the position of the prime, which is this one, number 2 here. That's the first position. So that's my local variables there. Now I'm going to use a while loop. In that in Pari GP, you say while, parenthesis, open parenthesis, close parenthesis. And whenever you do something in Pari GP, you have a line of code, you finish with semicolon here and here. So we're going to do the while loop for p less than or equal to the square root of n, which is what I have here, p less than or equal to the square root of n, and I'm using floor. This is probably not necessary, but I put it there just to make it an integer. So floor is basically taking the whole part of the number square root. In this case, it works like that because it's a positive number. And I put a comma here. So that will be the condition for the while loop. Now, the multiples here is the multiples of p, and this is how you construct multiples here. So it's going to be a list, which is open bracket, close bracket. Then we talked about this earlier. This is the pipe symbol, and these here are the numbers that I'm going to produce. So this is p squared k times p. I factored it just to put it a little bit better. So this is multiplication. So I want the list of all these elements. K here starts at 0 and ends at n. You can probably do better than n, but I'm just going to leave it there. And we're going to make sure that the number of those multiples is less than or equal to n. So we know we don't want to go above n. So that will give us all the multiples of p starting at p squared. Now what we do is we take the list and we delete the multiples. We can do that in Pari GP using this function called set minus. Set minus, what it does is the difference of the set, which is the elements that are in the list that are not here. So that will delete all the elements in the list that are from multiples. And that will update the list. And now I'm going to increase position because now we're going to look at the next prime. So that I'm going to say position plus plus, which will increase, for example, from position 1 to position 2. And I'm going to look at the next prime. So the next prime will be the number in the list in that position. So once you get position 2, it will give you the second prime in that list, which will be 3, and so on. And now, remember to put the semicolons here whenever you do a line of code. And the last thing that I'm going to do is I'm going to return the list, which is going to be the one that has only the prime numbers from 1 through n. So let's see how that works in Pari GP. So the code is already typed here in Pari GP already.
so I don't have to bore you typing myself all of that. Now the code for this particular algorithm is in the link in the video description for this video, so you're just gonna go and copy that if you want to use this implementation. So the only thing I have to do is just press enter right here, and that will give me the list that says that I already defined that function. So now you can just play with this. So let's say we wanna say, let's apply the sieve, let's say for the first 200 numbers, and that will give me the list of all the prime numbers less than or equal to 200. You can do this for larger numbers. It's not gonna be that much of slower actually than this. So for the 2000 number, that will be the list of all the prime numbers. So this actually is the implementation of the Sieve of Eratosthenes. That was the original algorithm that he published according to the historical records.
And that's all I have to say for today. Thank you for watching. Take care and good luck.